Ah, stars. Possibly some of the most beautiful objects in the universe. For as long as I can remember, I've been fascinated by them. From tiny red dwarfs that live for trillions of years, to enormous blue supergiants that shine with incredible power. Some stars are so cool that their surfaces are only around 2500 degrees Kelvin. Others can reach temperatures exceeding 50,000 Kelvin. Some are barely larger than Jupiter, while others are so gigantic that if they replaced our sun, they would extend beyond the orbit of Mars. And I can already see some of you thinking, wow, stars are amazing. I want to learn more about them. Well, you've come to the right place. I'm Coolalabright, and today we're going to explore the incredible world of stars. We'll learn what stars really are, how they form, the different types that exist throughout the universe, and how they eventually meet their end. So sit back, relax, and let's begin our journey among the stars. This is Coolalabright's Beginner's Guide to Stars. So let's get to the basics. What are stars really? When many people think of a star, they imagine a giant ball of fire floating through space. But stars aren't actually made of fire. Instead, stars are enormous spheres of plasma. Plasma is often called the fourth state of matter. Unlike solids, liquids, or gases, plasma consists of atoms that have been stripped of some of their electrons, creating an electricity-charged superparticles. You can find plasma here on Earth in lightning bolts, neon signs, fluorescent lamps, and even inside fusion experiments. But nowhere is plasma more impressive than inside a star. So what powers a star? To answer that question, we need to travel deep into the star's core. At the center of every true star, temperatures and pressures become so extreme that hydrogen atoms are forced together. When these atoms fuse, they form helium and release enormous amounts of energy. This process is known as nuclear fusion. Nuclear fusion is the engine that powers every star in the universe. It produces the heat, light, and radiation that makes stars shine. At the same time, a constant tug of war is taking place inside the star. Gravity is trying to pull the star inward and crush it. Fusion is pushing outward, resisting gravity's pull. As long as these two forces remain balanced, the star remains stable. Astronomers call this stable hydrostatic equilibrium. Eventually, however, the star will run out of fuel. When that happens, the balance is broken, and the next stage of the star's life begins. But before we talk about how stars die, let's first look at the many different kinds of stars that exist throughout the cosmos. Now that we know what stars are and how they generate their energy, let's take a look at the incredible variety of stars that are found throughout the universe. To do that, we're going to look at a diagram. This is the Hertzsprung-Russell diagram, usually shortened to the HR diagram, named after astronomers Ejnar Hertzsprung and Henry Norris Russell. This diagram allows scientists to classify stars based on their brightness and temperature. At first glance, the HR diagram may look confusing, but once you've recognized it, it becomes an incredibly powerful tool. Most stars, including our Sun, belong to a region called the main sequence. This is where stars spend the majority of their lives, steadily converting hydrogen into helium through nuclear fusion. Below the main sequence, you'll find white dwarfs, tiny but incredibly dense stellar remnants, left behind by stars like our Sun. Above the main sequence are giant stars and supergiants, stars that have exhausted much of their fuel and expanded to enormous sizes. And towering above nearly everything else are the hypergiants, some of the largest and most luminous stars known to the universe. But let's focus on the main sequence, because this is where most stars spend the vast majority of their lives. Astronomers divide main sequence stars into several main spectral classes: O, B, A, F, G, K, and M. A classic mnemonic used to remember this is, "Oh, be a fine girl, kiss me." Although modern astronomers often use alternative versions, the sequence itself remains the same. As we move from O-type stars to M-type stars, stars become cooler, smaller, dimmer, and generally less massive. Let's start at the smallest end of the scale. N-type stars, better known as red dwarfs, are the most common stars in our galaxy. These stars are tiny compared to our Sun, often possessing less than half its mass. Some have barely enough mass to sustain nuclear fusion at all. Red dwarfs are cool stars with surface temperatures ranging about 2400 to 3700 Kelvin. Because they burn their fuel extremely slowly, they are also the longest-lived stars in the universe. Some red dwarfs may continue shining for trillions of years, far longer than the current age of the universe. In fact, the universe is not yet old enough for a single red dwarf to have reached the end of its life. Some of the famous red dwarfs include Proxima Centauri, Barnard Star, Wolf 359, and TRAPPIST-1. Despite their abundance, red dwarfs are often difficult to see because they are so faint. Moving slightly upward, we arrive at K-type stars. These stars are often called orange dwarfs because of their warm orange coloration. K-type stars are larger and hotter than red dwarfs, but are still somewhat smaller than our Sun. They are often considered some of the best candidates for hosting life-bearing planets. Why? Because they live for tens of billions of years, giving life plenty of time to develop, while also being more stable than red dwarfs. Notable examples include Alpha Centauri b, Epsilon Eridani, and Epsilon Indi. Now, if I were an alien looking for a long-term home, a K-type star would definitely be high on my list. Next, we arrive at G-type stars. This is the category that includes our own Sun. Although they're commonly called yellow dwarfs, that's not entirely accurate. From space, the Sun actually appears white. Earth's atmosphere scatters sunlight, making it appear yellow from the ground. G-type stars have surface temperatures between roughly 5300 and 6000 Kelvin, and masses similar to that of the Sun. These stars remain on the main sequence for around 10 billion years before evolving into red giants. Some well-known examples include Alpha Centauri A, Tau Ceti, and 51 Pegasi. Of course, our favorite example is the Sun itself, a perfectly ordinary star that just happens to be our star. Slightly hotter and more massive than G-type stars are the F-type stars. These stars appear white to yellow-white and shine significantly brighter than the Sun. Their lifespans are shorter, usually lasting only a few billion years before exhausting their fuel. One famous example is Procyon A. F-type stars may not receive as much attention as some of the more extreme stars we'll discuss later, but they play an important role in the stellar family tree. Now we're entering the realm of the truly bright stars. A-type stars shine with a brilliant white color and have temperatures ranging from about 7500 to 10,000 Kelvin. Many of the brightest stars visible to Earth's night sky belong to this category. Examples include Sirius A, Vega, Altair, and Fomalhaut. These stars burn through their fuel much faster than the Sun, meaning that their lifespans are measured in hundreds of millions rather than billions of years. They're beautiful stars, but they live fast and die young. Now things start getting serious. B-type stars are much hotter, much brighter, and much more massive than our Sun. Their temperatures range from 10,000 to over 30,000 Kelvin. These stars emit enormous amounts of ultraviolet radiation and can shine thousands of times brighter than our Sun. Notable examples include Regulus, Acrux, and Spica. The most massive B-type stars will eventually explode as supernovae, enriching the galaxy in heavy elements forged in their cores. Finally, we reach the giants of the main sequence. O-type stars are among the hottest, brightest, and most massive stars in the universe. Their surface temperatures can exceed 50,000 Kelvin. Some are tens of times more massive than the Sun, and could be hundreds of thousands or even millions of times brighter. But all that power comes at a price. O-type stars burn through their fuel at an incredible rate. While red dwarfs can survive for trillions of years, O-type stars often live for only a few million years before ending their lives in spectacular supernova explosions. They're the rock stars of the stellar world, brilliant, powerful, and gone far too soon. And before we move on, we should mention one final category: brown dwarfs. Brown dwarfs are often called failed stars. They form in much the same way as stars, but they never accumulate enough mass to sustain normal hydrogen fusion in their cores. As a result, they occupy a strange middle ground between stars and planets. They're too massive to be planets, but not quite massive enough to become true stars. In a way, they're astronomy's ultimate almost success stories. Now that we've explored the different kinds of stars, it's finally time for the part we've all been waiting for: the life cycle of a star. Just like living things on Earth, stars are born, they grow older, and eventually they die. The difference is that stars live on timescales that are almost impossible for us to imagine. Some survive for millions of years, others endure billions, and a few make it to shining for trillions of years. To help us understand this journey, we're going to follow a star that I've named Isabel. Throughout this section, Isabel will be our guide as we watch a star's life unfold from beginning to end. Our story begins inside a giant molecular cloud. These enormous clouds of gas and dust drift silently through space and can stretch across dozens or even hundreds of light years. At first, everything seems calm, but appearances can be deceiving. Eventually, something disturbs the cloud. Perhaps a nearby supernova shockwave passed through. Perhaps two clouds collide. Or maybe gravity simply begins pulling material together in one region. Whatever the cause, the cloud starts to collapse. As gravity pulls gas inward, the cloud fragments into smaller clumps. One of these clumps will become Isabel. Over hundreds of thousands of years, more and more material falls toward the center. The pressure rises, the temperature rises, the collapsing cloud begins spinning faster and faster. Eventually, a hot, dense object forms at the center. At this stage, Isabel isn't a true star yet. She's a protostar, a stellar infant. She glows because of the gravitational energy, but nuclear fusion has not yet begun. For now, she's still waiting for her moment. And then, it happens. The core temperature reaches millions of degrees. Hydrogen nuclei begin fusing into helium. Nuclear fusion ignites. A star is born. Welcome to the universe, Isabel. For the next several hundred million years, Isabel enters the longest phase of her life, the main sequence. This is where stars spend the overwhelming majority of their existence. Every second, hydrogen atoms inside Isabel's core fuse into helium. The energy release pushes outward. Gravity pulls inward. The two forces balance perfectly. As long as this balance remains intact, Isabel remains stable. Day after day, year after year, millions after millions of years, life is perfect. If planets orbit Isabel, this is the period where life would have the best chance to emerge. But eventually, even stars run low on fuel, and Isabel's hydrogen supply is slowly running out. After roughly 1 billion years, changes begin deep within Isabel's core. The hydrogen field that once powered her is becoming scarce. Without enough outward pressure, gravity gains the upper hand. The core begins to contract. As it shrinks, it becomes hotter, much hotter. The rising temperatures ignite fusion in surrounding layers of hydrogen. The result is dramatic. Isabel begins to expand, and expand, and expand. Soon she swells to dozens, perhaps hundreds of times her original size. She has become a red giant. Despite the hotter core, her enormous surface area causes her outer layers to cool, giving her a reddish appearance. If Isabel had planets nearby, this would be bad news. Very bad news. Any worlds orbiting too close would likely be engulfed entirely. At this point, Isabel is no longer the calm, stable star she once was. She has entered old age, and a final chapter is approaching. As an A-type star, Isabel belongs to the category astronomers call intermediate mass stars. This means she won't die in a supernova. Instead, she faces a quieter, but still beautiful ending. Inside her core, helium begins fusing into heavier elements such as carbon and oxygen. For a time, the star finds stability once again. But eventually, that fuel runs out as well. Unlike massive stars, Isabel doesn't have enough mass to continue fusing heavier elements indefinitely. The core can no longer support itself. The outer layers become unstable, pulses and stellar winds begin blowing material into space. Slowly, Isabel sheds atmosphere. The surrounding gas expands outward, forming an enormous glowing shell. This structure is called a planetary nebula. Despite the name, it has absolutely nothing to do with planets. Early astronomers simply thought these objects looked like planets through their telescopes. At the center of the nebula remains Isabel's exposed core, a tiny but incredibly dense stellar remnant, a white dwarf. Imagine squeezing a mass similar to that of the Sun into an object roughly the size of Earth. That's a white dwarf. A single teaspoon of its material would weigh tons. Isabel's nuclear fusion has finally ended. But the story isn't quite over. White dwarfs no longer generate energy through fusion. Instead, they slowly radiate away their remaining heat. Over billions of years, Isabel gradually cools. Her bright white glow fades, and fades some more and more. Eventually, after an unimaginably long period of time, she will become a cold, dark remnant, known as a black dwarf. However, there's a small problem. The universe is only about 13.8 billion years old. That's nowhere near long enough for a white dwarf to cool into a black dwarf. As far as we know, black dwarfs don't exist yet. The universe simply hasn't been around long enough. So for now, white dwarfs are where the story ends, at least until the distant future. Now Isabel's story is over, but not every star follows the same path. The most massive stars experience a far more violent rate. Instead of becoming planetary nebulae and white dwarfs, they evolve into enormous red supergiants. Inside these stellar giants, fusion continues creating heavier and heavier elements. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, oxygen becomes silicon, and eventually silicon becomes iron. That's where the trouble begins. Iron is a dead end for fusion. Fusing iron consumes energy rather than releasing it. Once an iron core forms, the star's fate is sealed. Gravity suddenly wins, the core collapses in a fraction of a second, temperatures soar, pressure skyrockets, and then a supernova. For a brief period, the dying star can outshine an entire galaxy. Your explosion blasts newly formed elements into space, where they may someday become planets, oceans, mountains, and even life itself. What's left behind depends on the star's mass. Some leave behind neutron stars, objects so dense that a single teaspoon would weigh billions of tons. Others collapse even further, creating one of the most mysterious objects in the universe, a black hole. And thus, the life of a star comes to an end, but its material lives on, helping create the next generation stars, planets, and perhaps even civilizations looking up at the night sky and wondering where they came from. And with that, our journey through the lives of stars come to an end. Today, we've explored some of the most incredible objects in the universe. We've learned what stars really are, discovered the many different types of stars scattered throughout our galaxy, and followed a star from their birth inside a cold molecular cloud all the way to their final days as a white dwarf. Perhaps the most amazing thing about stars is how they live. It's what they leave behind. Every atom of carbon in your body, every atom of oxygen that you breathe, the calcium in your bones, the iron in your blood, all of these elements were forged inside stars that lived and died billions of years before our solar system was even born. In a very real sense, you and I are made of stardust. The same processes that created the stars in the night sky also helped create you. And I think that's pretty amazing. So the next time you step outside on a clear night, take a moment to look up. Some of those tiny points of light may be red dwarfs that will outlive our sun by trillions of years. Some may be massive blue stars racing towards spectacular supernova explosions. And some may already be gone, their light only now arriving at Earth after traveling across the vastness of space. Each one has its own story, a beginning, a life, and an ending, just like Isabel, and just like us. The universe is filled with countless stars, and we've only scratched the surface of what there is to learn about them. But hopefully, this guide has helped you to take your first step into the fascinating world of astronomy. Thank you so much for joining me on this journey. If you enjoyed this video, be sure to leave a like, subscribe to the channel, and turn on post notifications so you don't miss any future uploads. I'm Coolalabright, and until next time, keep looking up, and I'll see you among the stars. Peace out.